Hey everyone, this is my Physics 2212 Lab 2. So to start off, the goal of this experiment is to measure the magnetic field generated by a small bar magnet, specifically observing how field strength changes with distance. We'll be conducting this experiment using a basic bar magnet along with a magnetometer app from a smartphone. After this, we will compare our experimental data using magnetic dipole field equations and the Biot-Savart law in GlowScript. And here's a brief preview of our results down here at the bottom. Mu equals 2.03. We got that from our experimental model, and our computational model, we got 1.8 A times meter squared. Here's the key principles that we use. These are equations that we use in our coding and our calculations. We had the Biot-Savart law. We have the magnetic dipole field, and then our distance dependence equations over here. This was used for our graphing. The distance dependence equations were with the data that we collected, like the distances and the magnetic fields we got from the x components and the y components from our magnetometer app. Here's the experiment. This experiment required us to measure the magnetic field produced by a bar magnet at various distances using an iPhone magnetometer. To do this, we isolated the magnet from Earth's magnetic field. We aligned the magnetometer with the bar magnet and took off on-axis and off-axis measurements. We recorded components of magnetic field at specific distances. We subtracted Earth's magnetic contribution and determined the exponent in the relation B equals KR to the power of N. Here's the assumptions that we made. We're treating the bar magnet as a magnetic dipole. There is no nearby magnetic interference, and precise alignment and orientation were the assumptions we had for this experiment. And for our system and surroundings, the system is the bar magnet and the field that it generates, and our surroundings are Earth's magnetic field, the magnetometer of the smartphone, and the environment, which is like things like the table, air, or the nearby magnetic materials. Here's our measurements here. This is the data we recorded from our experiments. We have our distances and our magnetic fields. And this line right here is what we got from our ln function. And our slope was negative 3.1728, which is our n value in the previous equation that I mentioned. And our ln k value is negative 14.75. And just a few things to note. When the magnetometer moves away from the magnet, it begins to measure a near zero magnetic field in the x direction. And when it moves closer to the magnet, the x component increases. Here's our calculations from the experimental model. We ended up getting mu equals 2.03 A times meter squared. And here's how we did it over here. We have our distance dependence equations right here. We plugged in the values that we got from our graph, from the line, the linear model. And then here's the magnetic field of a dipole on axis. And this is our equation that we discussed before. And we ended up getting this number here, 4.093 times 10 to the negative seventh. And then we plugged that value in down here for calculating our dipole moment, and we got 2.03, and that's how we got that answer. Here's our computational model. Here's this top picture shows us how we created the magnet at the origin. The magnitude of the magnetic moment from our experiment is plugged in right here, and the function for our magnetic field is the most important part, and we plugged in that function here. And here's how we created our arrows and such down here for our model. And here's how we visualize the magnetic field at 45 degrees. These are equations down here. And here's our results. We ended up getting our perp locations and coordinates here on our axis. And our D value is 2.61205 and B at 45 degrees at a distance D. You can see that here. Our magnitude B is 1.8 times 10 to the negative 5, which we got in the start. Here's our sources of error. For both our models, it must be noted that there's much more room for error during the experimental model rather than the computational model, and this is due to factors such as sensor inaccuracies, misalignment, nearby magnetic fields, or inaccurate distance measurements. However, when you look at the spreadsheet value, B is measured in the same value from the code, which is the magnitude of B 45 degrees, we see that the values are very close to each other here. And you can see these images from the screenshots of our code and our graph. So here's our discussion. What if, in our experiment, we oriented our setup so as to compensate for magnetic north? What if we hadn't done that? If the meter stick were not aligned east to west, the magnetic field would not be orthogonal to Earth's field, and this would result in vector superposition of the Earth's magnetic field with the bar magnet's field. What if you redid the experiment, but instead of using single magnets, you use two identical magnets stuck together end to end? How would you expect your measurements to differ? Stacking two magnets end to end like this would double the magnetic dipole moment and would increase the strength of the magnetic field. However, our observation locations would still be the same after this. And that's all I have. So thank you for watching.